Hello students, let us continue discussion about transient conduction. In this lecture, I will be talking about solving transient conduction problems if the Biot number is greater than 0.1. So in this case, what we have to do is, here to explain the concept, I am considering a plane ball. The same analysis is applicable for cylinder as well as sphere. Here, I have taken the thickness of the plane wall as 2L, and at the center I have written the axis. On either side, we have a fluid which is having a temperature of TA and a heat transfer coefficient of H. The heat is being transferred to the fluid from the solid. In this case, we can write the general differential equation for one-dimensional heat conduction with transient conduction, that is varying temperature with respect to time, as d square T by dx square is equal to 1 over alpha into dt by d tau. This is applicable in the range 0 to L within the medium for time greater than 0. Now we need to discuss about the boundary conditions, the initial and boundary conditions for this problem. There are three conditions. One is the initial condition at tau equals 0, that is at the beginning of the heat transfer process. Within the body, wherever I measure the temperature, it will be Ti. So that is given here. At tau equals 0, from 0 to L, the position of x varies from 0 to L, 0 being the center here and L being the outermost surface. The temperature will be equal to Ti. Once the heat transfer starts, then we have two boundary conditions. One is at x equals 0, that is at the axis, dt by dx will be equal to 0. For any given time, dt by dx will be equal to 0. That is, at the axis, there is no change of temperature with respect to the position. And then the second condition is at the surface, the heat is being transferred out of the body through convection. So at the surface, that is x equals L, for any time greater than 0, minus k into dt by dx will be equal to h into t minus dA. So what is the amount of heat conducted? That will be equal to amount of heat conducted out of the body. This term involves infinite series when we expand it using Taylor series. So it is difficult to solve these kind of problems. So what we do is we try to write them in the form of a table, or we try to represent the same in the form of a chart. So for that, what we do is, first we write dimensionless parameters. So we have dimensionless temperature as theta x comma tau, which is equal to T of x comma tau minus Ta divided by Ti minus Ta. In this case, I am writing T of x comma tau because temperature depends on one of the spatial coordinate as well as tau. In the lump system analysis, we had seen that the temperature within the body remains almost same. There will be no variation of temperature with respect to spatial coordinates. So there we had written just T tau, because temperature depends only on time, not on the position. But if the Biot number is greater than 0.1, then the temperature also depends on the position. Here we are dealing with one-dimensional transient conduction, so I am writing T of x comma tau. So dimensionless temperature is theta x comma tau is equal to T of x comma tau minus Ta divided by Ti minus Ta, and dimensionless distance from the center is capital X, which is equal to small x by L. Then the dimensionless heat transfer coefficient is our Biot number, which is h into L by k. In this case, the definition of L changes. The definition of characteristic length, L is half of the thickness for plane slab and R for cylinder as well as sphere. So you need to remember this. Once we find out the Biot number using h into LC by k, where LC is the characteristic length, if its value is greater than 0.1, then what we have to do is we need to find out the Biot number again using the definition of L given here. L will be half of the thickness for Plains law. So the Biot number remains same for both the cases. But for long cylinder and sphere, since the characteristic length now which we have to take is radius, not r by 2 or r by 3. Here the value of Biot number changes for long cylinder and sphere. And then we find out dimensionless time, that is given by alpha tau by L square, which we call it as Fourier number. This is another important dimensionless number in transient conduction. So with these definitions of dimensionless parameters, now let us apply a method called one-term approximation. So here it has been observed that after finding out experimental results, if the Fourier number is greater than 0.2, then we can in the Taylor series expansion we can use only the first term, and we call that as one-term approximation because we are using only the first term of the expansion. And when we apply that and simplify, then we get for a plane wall the dimensionless temperature, that is T of x comma tau minus Ta divided by Ti minus Ta, will be equal to A1 into e to the power of minus lambda 1 square into f naught multiplied by cos of lambda 1 x by L excuse me, for Fourier number greater than 0.2. And for long cylinder it is theta r comma tau will be equal to T of r comma tau minus Ta divided by Ti minus Ta, and that is also equal to A1 into e to the power of minus lambda 1 square into f naught into j naught of lambda 1 r divided by capital R, that is the outer radius. And for sphere, again the dimensionless temperature will be equal to A1 into e to the power of minus lambda 1 square into f naught multiplied by sine of lambda 1 small r divided by capital R divided by lambda 1 r divided by capital R for Fourier number greater than 0.2. We don't have to remember these equations because we are not going to solve problems using one-term approximation method. But what you have to note here is the value of A1 and lambda 1 will be tabulated, and depending on the type of problem we are going to solve and the different parameters, we need to choose the value of A1 and lambda 1 from the table. So once we choose the value of those two, then we can easily find out the dimensionless temperature, and then from that we can find out the heat transfer rate and the total amount of heat removed or added to the body. In our syllabus we have graphical method. So to solve graphical method, first let us see the type of graphs. I think all of you are familiar with this graph. It's a normal graph or a linear graph where the x as well as y axis as well as y axis has the same unit of dimensions. But in our transient conduction we will not be using a regular graph, or the data will not be represented on a regular graph, because here the values ranges from 1 to maybe million or billion. So it will be in the form of 1, 10, 100, 1000, 10,000 like that. So it will be multiples of 100. So for that purpose we go for semi-log graph. So here you can see that the y-axis remains as it is. It's a linear graph in y-axis, the dimensions are linear. But when you see the x-axis, you can see that the units are not constant. So here we have 1, 2, 3, 4, and the distance between 1 and 2 and 2 and 3 and 3 and 4 are different. As we move towards 10, the distance between the units will be reducing, and then we will get to 10. From 10 we will not start with 11, we will start with 20, 10, 20, 30, 40 till 100. And every time as we move away from the base position, that is maybe 10, 100 or 1000 or 10,000 or 100,000 or 1 lakh, the distance between the consecutive units keeps on reduces. You can notice that in the table below. So in this table I have taken the regular scale, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I have found out the logarithmic value of that. So log of 1 for base 10 is 0, log of 2 is 0.301, then log of 3 is 477, and for 4 it is 0.602, then 5.699. So here you can see that the difference between the consecutive values are reducing. That is what happening here in the graph. So this is the scale which we are going to use. Once we reach 10, 10 is 1, and then for 20 it is 1.301. You can see that it is same, the distance between, if I take the difference between 1 and 2 and 10 and 20, the dimension is same, that is 0.301. Similarly for 30 and 3 it is same, for 40 and 4 it will be same. So that is how we have the semilog graphs are drawn. So now we will be using this semilog graph when we are dealing with the charts given for transient conduction. So before going to the charts, these charts are called Heisler and Grober charts because those are the people who drew this chart. So before going to that, we need to look into the formulas which we will be using in finding out the different values using the graphs. So for that, first one is in your data handbook, the page number is 63. So here we have transient conduction, infinite solids, and this entire tabulation is for plane wall. Then we have similar correlations for cylinder as well as sphere. Okay, here you can see that the plane wall, at the center we have the axis, and from here the value of x, that is the origin, and on either side the thickness is L. On either side the surface is covered with a fluid which is at T infinite temperature. So instead of TA, here they are using notation T infinity, and it is having a heat transfer coefficient H. So the first relation which we need to remember, which we need to look at is for the center plane temperature. So that is the temperature at the center. The temperature at the center we call it as T0. So on the third column you have all the notations and their abbreviations, so you can go through that. So T0 is the center plane temperature. So to find out that, we have another we have a chart on page number 65. We need to refer that chart, and then if you want the temperature at any other position, maybe somewhere here if I want temperature, or maybe somewhere here very close to the surface if I want to know the temperature after a certain duration of time, then for that we need to use T of x comma L, this relation T of x by L minus T infinity divided by T0 minus T infinity. So here you can see that in the denominator we have T0 minus T infinity. So to find out the temperature at any other position, we need to know the center line temperature or the center plane temperature. So first we need to find out the center plane temperature using this relation, the first relation, and then we have to use this the second relation to find out temperature at any other distance. Again, the ratio of this temperature will be provided in the page chart which is presented page number 66. And then we need to find out the heat transfer through this. So for that we have the relation here. So here we have to find out the total heat flow, Q by Q0 will be equal to the ratio will be given in chart which is present in page number 67, and the relation for Q0 is given here, that is rho C into L into Ti minus T infinity or Ta in our notations, and instantaneous heat transfer rate, that is small q will be equal to H into A into T tau minus T infinity. So we can find out the instantaneous heat transfer rate using this. So below that you have relations for long cylinder, and in the next page you have relations for sphere. Now let us look at the chart. First let us look at the chart for center plane. So here you have the chart for infinite plate. So the name of the chart is infinite plate temperature time history at mid plane. And if you observe the x-axis, in the x-axis we have the Fourier number, and the x-axis is semi-log, and we have different curves for different values of Biot number. So here you have h into L by k. This is for the new definition of Biot number, where L will be half of the thickness for plane wall and radius for cylinder as well as sphere. And on the y-axis we have the temperatures which we have to measure, or the temperature ratio which we need to find out. So in this case what we have to do is, first we need to find out the Fourier number. So once we know the Fourier number and Biot number, then if the Fourier number is 10 and the Biot number is 0.1, then from 10 you need to draw an imaginary line vertically up where that intersects the curve for 0.1. From there you need to draw an horizontal line. Again, when in your examination you should not write on your data handbook. You have to just note where the point intersects with the curve, and from there you need to come horizontally to the y-axis. So here you will get the temperature ratio. Using this temperature ratio you will be able to find out the temperature at the center. Then the second graph for the plane wall is the plane infinite plate temperature time history at any position L. So if you observe this graph, on the x-axis we have the Biot number. On the x-axis we have the Biot number h into L by k, and we have different curves for different values of x by L. So now I have to find out the Biot number. So I'll be knowing the Biot number. Maybe 0.1 is on the y-axis, 1 is here. So if our Biot number is 1 and x by L ratio is 0.6, then here we have the 0.6 curve. So now where these two lines intersect, there I have to draw an horizontal line and find out the temperature ratio at that location. So once you know that, then you can use T x by L minus T infinity divided by T naught minus T infinity relation to find out the temperature. And then to find out the total heat flow, so we have this graph. So the name of the graph is heat flow infinite plate. For cylinders it will be heat flow long cylinder, and for sphere it will be heat flow sphere. So here in the x-axis we have Bi square into F naught, that is Biot number squared into F naught. So I have to find out that. And here you have 10 to the power of minus 4, 10 to the power of minus 5, 10 to the power of minus 3, 10 to the power of minus 2, and 10 to the power of minus 1. 10 to the power of minus 1 is nothing but 0.1. 10 to the power of minus 2 is 0.01. 10 to the power of minus 3 is 0.001. So depending on what you get, either you can move towards left or you can move towards right. Then we have 10 to the power of 1, 10 to the power of 2, that is 100, 10 to the power of 3, 1000, and 10 to the power of 4, 10,000. So these are very large numbers. This cannot be accommodated in a regular graph. That's why we are using semi-log graph here. Once you find out Bi square into F naught, then we have different curves for different Biot numbers. So here we have Bi is equal to h into L by k. If my value of Bi square into F naught is 10 and my Biot number is 5, from 10 I'll draw a vertical line, and the Biot number 5 curve is here. So where they intersect, from there I will draw a horizontal line on the y-axis, and on the y-axis we have Q by Q naught. So once you get that ratio, then you need to find out Q naught using the relation given in the data handbook in page number 63. From that we can find out the total heat flow Q, and once you know the temperature, then you can find out the instantaneous heat transfer rate if required. Now let us try to solve problems. In the first problem, a 50 mm thick iron plate, K equals 60 watt per meter Kelvin, Cp equals 460 joule per kg Kelvin, rho equals 7800 kg per meter cube, and alpha equals 1.6 into 10 to the power of minus 5 meter square per second, is initially at 225 degrees Celsius. Suddenly both surfaces are exposed to a fluid at 25 degrees Celsius with a heat transfer coefficient of 500 watt per meter square Kelvin. Calculate the center and the surface temperature 2 minutes after the start of cooling begins using Heisler's chart. Also calculate the total heat transfer after 2 minutes. So for this, first let us list out the data. The data are: the geometry is a plane wall or an infinite wall, and the thickness of the slab is 2 times of L in our convention. So 2L is 50 millimeter, so L will be 25 millimeter. And Ti, the initial temperature is 225 degrees Celsius, the fluid temperature is 25 degrees Celsius, heat transfer coefficient is 500 watt per meter square Kelvin, and alpha is 1.6 into 10 power of minus 5 meter square per second. Thermal conductivity is 60 watt per meter degree Celsius, and specific heat is 460 joule per kg Kelvin. Now what we have to do is, we need to find out the center temperature and the surface temperature after 2 minutes. So T0 and TL after 2 minutes, and then we need to find out the total heat transfer after 2 minutes. So Q total after 2 minutes we need to find out. For this, first let us find out the Biot number. Biot number, we need to use the usual notation H into LC by K, where LC is half of the thickness for plate, that is 25 millimeter here. So the Biot number is 0.2083, which is greater than 0.1. So we cannot use lump system in this case, and we have to go for Heisler's chart method to solve the problem. Now what I'll do is, I'll find out the temperature at the midplane, that is at the center. For that purpose, I'll find out the Biot number again with the new notation, where L is half of the thickness. So the Biot number in this case remains same, but for cylinder and sphere it changes. And I'll find out the dimensionless time, that is Fourier number. I know time as 2 minutes, so tau will be 120 seconds. When I substitute the values, I'll get the Fourier number as 3.072. And with that, I'll go to infinite plate temperature time history at mid plane, and for Fourier number of 3 on the x-axis we have Fourier number, and we have different curves for different Biot numbers. For Fourier number 3 and Biot number 0.2, where those two intersect, I will draw a horizontal line, and I can see that it is 0.58. So here on the y-axis we have 0.5 and 0.6. In between those two we have 5 subdivisions. So each subdivision will be 0.02. So it is 0.52, 0.54, 0.56 and 0.58. Then we have 0.6. So I can see that the horizontal line is coinciding with 0.58. So I'll take the ratio as 0.58, and from that I'll find out T0, because I know TA and TI, so I need to find out T0. So T0, I'll get it as 141 degrees Celsius. Once we are done with this, now I need to find out the temperature at the surface. For that I need to use the second graph. So to find out the temperature at the surface, I need to find out x by L, the dimensionless distance. So x by L will be, again x as well as L in this case is same, that is 25 millimeters. So I'll get it as 1. And from the infinite plate temperature time history at any position x, so I know x by L ratio as 1 and Biot number as 0.2083. So here on the x-axis I have Biot number, and I have different curves for x by L ratios. So for Biot number of 0.2 and x by L of 1, I'll where those two intersect, I'll draw a horizontal line, and that reaches the y-axis at 0.9. So now the temperature ratio, so here the temperature ratio x by L minus TA divided by T0 minus TA is 0.9. I know T0, which we have calculated in the previous step, and I know TA, that is given 25 degrees Celsius. From that I can find out the surface temperature, that is 129.4 degree Celsius. Once we are done with this, now we need to find out C, that is total heat transfer for the first 2 minutes. Again, for that what I will do is I need to go for the heat flow infinite plate. For that, first I need to find out Bi square into F naught. Here the Biot number is 0.2083 and Fourier number is 3.072. So when I calculate Bi square into F naught, so Bi square into F naught, I will get it as 0.1332. So now I will go to the chart. In the chart, in the x-axis we have Bi square into F naught. I had a value of 0.1332. So 0.1332. Here we have 0.1. Then the next will be, so we have 0.1 and next will be 0.2. In between these two I have 0.1332. So I have approximately drawn a vertical line here, and I have drawn this till it reaches Biot number of 0.2. So on the y-axis we have different curves for Biot number. So where those two intersect, I have drawn a horizontal line, and here I can see that in the y-axis I have 0, 0 and then 0.2. Then the mid one should be 0.1. So then 0.3, 0.4 and 0.5. And since this horizontal line, the black line, is lying in between those two, I have taken the ratio as 0.45. So once you find out that ratio, now we need to find out Q naught, and the equation for Q naught is given in page number 63. In PDF the page number is 71. Q naught is rho Cp into L into Ti minus Ta. So when I find out that, it is 17.94 megawatts, and when I substitute that in this equation to find out the total heat flow, so total heat flow is 8.073 megawatts. So this is how you need to solve problems using the charts. We will solve one more problem for cylinders. So in this problem we have a long cylinder of 12 cm in diameter and initially at 20 degrees Celsius is placed into a furnace at 820 degrees Celsius with local heat transfer coefficient of 140 watt per meter square Kelvin. Calculate the time required for the access temperature to reach 800 degrees Celsius. Also calculate the corresponding temperature at the radius of 5.4 cm at that time. Also calculate the total amount of heat added to the cylinder at the same time period. Take alpha equals 6.11 into 10 to the power of minus 6 meter square per second, K equals 21 watt per meter Kelvin, and C equals 460 joule per kg Kelvin. In this case we are taking a cylindrical workpiece and we are keeping that in the furnace. Initially the workpiece was at temperature 20 degrees Celsius. It has a diameter of 12 centimeter, and the heat transfer coefficient between the workpiece and the furnace gases will be 140 watt per meter square Kelvin. The alpha is 6.11 into 10 to the power of minus 6 meter square per second. Thermal conductivity is 21 watt per meter degree Celsius, and specific heat is 460 joule per kg Kelvin. So here also we need to find out three parameters. One is the time required for the center temperature to reach 800 degrees Celsius. In the previous problem they had given us the time, we had to find out the temperature, but in this problem they have given the temperature, we need to find the time. So it's the reverse method of that. Then we need to find out the temperature at a radius of 5.4 centimeter at the same time period, and then we need to find out total heat transfer, the amount of heat added to the workpiece at the same time period. First let us find out the centerline temperature, and before that we need to find out the Biot number. Here Biot number is H into LC by K, where LC is R by 3 for cylinders. So when I do that, I'll get a Biot number as 0.1333, which is greater than 0.1. So we have to use charts. Now let us find out the centerline temperature. Now in this case, to find out the centerline temperature, I need to find out the Biot number again with the new notation, where L will be equal to radius for long cylinders as well as sphere. So Bi will be equal to H into L by K, where L is, since the diameter is 12 centimeter, the radius is 6 centimeter. So when I do that, I'll get the Biot number as 0.4, and this Biot number should be used in the graphs. So whenever you are referring to graph, you have to use this Biot number. Now I cannot find out the Fourier number or the dimensionless time because I don't know the value of time. I need to calculate the time. So what I'll do is, since I know the temperatures, I'll find out the temperature ratio from the given temperatures, and then I'll go to the chart. So here the Biot number is 0.4 and the temperature ratio is 0.025. So if you observe the y-axis, we have 0, and then we have 5 divisions, then we have 0.1. So each division will be 0.025. Sorry, 0.02. We have 0, then 0.02, 0.04, 0.06, 0.08 and 0.1. Then after that 0.1, 0.12, 0.14, 0.16, like that. So approximately just above 0.02 I have drawn a horizontal line, and now I am moving in this direction. I am moving towards right till it reaches the 0.4 curve. So where it reaches 0.4 curve, this is the 0.4 curve. Where that reaches the 0.4 curve, there I'll draw a vertical line and I'll try to find out the Fourier number. So in this case the Fourier number is approximately 5.6. So we have 4, and then the next bright line is 5, and after that we have 6. So in between that, it is approximately, the vertical line is approximately on the third vertical line in the graph. So I have taken it as 0.56. Once I know Fourier number, then I can find out the time, since Fourier number is equal to alpha tau divided by L square. So the time in this case is 3299.5 seconds. Now I need to find out, after 3299.5 seconds, I need to find out the temperature at a radius of 5.6. So I'll find out small r by capital R. Small r is the radius at which you need to find out the temperature, and capital R naught is the outer radius. So 5.4 divided by 6 will give me 0.9. Now I'll refer to the second graph, that is at any radius. I'll just clear this notations. Okay, now I'll refer to the second graph, long cylinder, temperature, time history at any radius. And here on the x-axis we have the Biot number, and on the y we have different curves for r by r naught values. So I'll locate a Biot number of 0.4 on the x-axis. From there I will draw a vertical line where till it reaches 0.9 curve on the graph. Where it reaches 0.9 curve, then from there I will draw a vertical the horizontal line to y-axis. And now when I do that, I'll get a ratio. Here you can see that it is in between 0.8 and 0.9. So you can take it as 0.85 approximately. And once we know that value, then I can find out the temperature at the given radius. So the temperature at the given radius is 803 degrees Celsius. Once we do this, then now we need to find out the heat transfer rate. For heat transfer rate, again I need to refer to the graph. So before that, here I need to find out bi square into f naught. Biot number is 0.4 and f naught is 5.6. So when I do that, I'll get it as 0.896, which is very close to 0.9. Now I'll refer to the chart. So now I need to locate on the x-axis 0.896 and on I need to locate 0.4 0.4 Biot number curve. So when I see that it is very close to 0.9 on the x-axis, so as we move towards the end of that unit, that will be very close to the next digit, that is 1. So I have drawn a vertical line here, and 0.4 Biot number curve will be somewhere here. So that will be out of the graph. So somewhere here you will get 0.4 curve. So that will not intersect in our case within the graph. So I have taken the ratio as since we have reached the maximum height, I have taken the ratio as 1 for q by q naught. Since q by q naught is 1, if I calculate q naught, then I will be able to find the same can be used for q. So q naught for a cylinder is rho Cp pi into r naught square into Ti minus Ta. This is given in page number 64. And now I need density, but the density is not given in the problem. So they have given only alpha, K and Cp. And I know the relation between them. I know alpha equal K by rho Cp. So using that, I will find out the density. So density will be equal to 7471.7 kg per meter cube, and I'll substitute that in q naught equation. Again, in q naught equation we have a negative sign, so you can see it here. So here you have a negative sign, so I'll use that. So when I substitute the value, I'll get q naught as 31.1 megawatts, and that since q by q naught is equal to 1, so q will be equal to 31.1 megawatts. So this is how we need to solve a long cylinder problem using charts. So in the case of charts also, either the temperature will be given, we need to find out the time, or the time will be given, we need to find out the temperature. And for any if you want to find out the temperature at any distance from the center or at any radius from the center, then you need to know the center temperature. Without that, you won't be able to solve the problem. So in those cases, the first thing which you have to do is you need to find out the temperature at the center. Thank you.